Hello, everybody. So thanks for coming to my talk. So my talk is titled Feynman Diagrams from Conformal Integrals. So the idea is that we'll be looking at Feynman diagrams, the usual Feynman diagrams in momentum space, and we'll be seeing how we can get them from conformal integrals, which one encounters in the study of conformal field theories when you're computing conformal blocks and correlators in conformal field theories and so on. So the objects of interest are the Feynman diagrams. We'll concentrate on the ones with massless internal lines. So they look like this. You might have already heard about these in the talk by Ekta and so on, where the objects to consider are these. Usually in a course in QFT, you will consider these guys with delta is equal to 1. But the ones with general delta is are the ones that are useful in computing all sorts of Feynman diagrams, especially when you look at tensor Feynman integrals, you want to convert them into scalar ones, or you want to use this integration by parts method, which relates Feynman diagrams with different delta i's. So these are the objects of interest. In particular, let's look at one loop Feynman diagrams, which take this simpler form, where the propagators are now these L minus pi squared. L is the loop momentum that you want to integrate over, and these pi's are these momenta that are running inside the lines. And they're related to the external momenta in this way when you impose momentum conservation at each vertex. So what we'll do in the rest of the talk is we will look at when we'll draw diagrams without the external lines, because the same integral will stand for a diagram like this with any number of external lines, and the momenta of the momentas that are going in the denominator here get related to the ones that are external by momentum conservation. But so we'll look at these sort of integrals, and so we'll forget about the external lines for that reason. Okay, so the idea is to get these from conformal integrals, and the way we'll do it is by first going to position space and considering position space correlators and working with them, and then we'll come back to momentum space and see how that helps us to get answers for Feynman diagrams from conformal integrals. So we'll look at massless flat space correlators in position space, and for today's talk, these are useful to get to this relation between conformal integrals and momentum space Feynman diagrams. But I'm interested in them more generally because I would like to study correlators in flat spacetimes, and they are useful. They're useful objects to study to try and understand how information in the bulk of flat spacetime is encoded on its boundary and so on. I won't get to that story today, of course, but just to say that they have independent interest for that reason. Usually when we do QFT, we do it in momentum space and flat space, but one would like to do it in position space with this intention also, because you want to be able to compute bulk space-time correlators and then take their boundary limits, take their extrapolate limits, and that helps you get to various results about how information is contained in the boundary of flat space-time and so on. So you want to be able to compute flat space correlators first in the bulk and then be able to take them to the boundary where then they are correlators defined on let's say the null infinity or in spatial infinity of flat spacetimes. Recently also we gave a formula for how to compute the S matrix in position space, and that was done in collaboration with these authors, where we gave a formula for the S matrix in terms of the path integral as a function of boundary values of fields, and we showed that one can compute the S matrix as singularities of correlators and so on. So for these reasons also, one is interested in computing these position space correlators. So that was my quick motivation. Now let me get into how these flat space correlators can be computed and how they can be computed as limits of conformal correlators. So let's start with the most simplest one, which is a contact correlator. So you want to be able to compute this guy, which is now a function of these delta i's from delta 1 to delta n, and the propagators go like x minus y squared, and you want to do an integral over y, which is in the bulk of flat spacetime. Okay, so one does this by going into the Schwinger representation, which was alluded to, I think, in Johannes' talk, where you get a form like this, and these are now functions just of these Sij's, which are Lorentz invariants, xi minus xj squareds, and you want to be able to compute these sort of integrals. So how do you do them? One nice property that you can note of this integral is if all these delta i's are such that the sum delta 1 to delta n equals the space-time dimension, then the integrand has a conformal covariance. So if you just take this integrand here and perform an inversion on it, you will see that in this case where all the sum of all deltas equals d, you will just pull out an overall factor of x1 squared to the delta 1, x2 squared to the delta 2, and so on, product like that. Okay, that only happens if the sum of all the delta is equals d. So if that is true, we will call such correlators as conformal correlators because they have this conformal covariance property. And so let's first compare these two sets of correlators, the ones which have sum over delta equals d and the ones which do not. Okay, so here's a table to compare them. And the ones on the left are these conformal correlators. So once they satisfy these conformal constraint, what happens is that the form looks like this. So there is an overall H function which depends on these Sij's, which are these Lorentz invariants, xi minus xt squared, times what are called D functions. So I'm calling them D safety here because I'm going to contrast them with the D functions that appear on the right-hand side. And these D functions are functions of the cross ratios. Because of this conformal covariance property, they'll only depend on the cross ratios. And on the right side, we have the ones which do not have this conformality constraint. And these will turn out to be functions of simple ratios, not the cross ratios. Now, a very nice property that you will note if you count the number of cross ratios versus the number of simple ratios, is that the number of cross ratios of n plus 1 points equals the number of simple ratios of n points. Okay, so you can do the counting and see that this match happens. And physically, what is happening is that if you take n plus 1 points in a conformally covariant theory, and you put fix one point to be let's say at infinity, and you ask what are the residual symmetries that will keep this point at infinity but can move things around, you will see that those are the symmetries on the right side that you get. So only the special conformal transformation will bring back some point, but the rest of the transformations will not. So for that reason, this statement here is true. And in fact, more is true. So if you look at, let's say, a specific example here between a 4-point conformal correlator where you have this H function and this is the D function. What happens is that the D function you get for the 4-point conformal correlator is exactly the D function that you get for the 3-point non-conformal correlator. Okay, so you see this relation between the two. You just substitute the cross ratios with the simple ratios, and then you see these two match. So in fact, we showed that at the level of the correlator, this is true. So if you take the full correlator, or the 4-point correlator, and you take 1 point and you put it to infinity, you will recover the 3-point non-conformal correlator up to this overall factor. And this is, I won't show the proof here, but this is true for any contact correlator, that if you want to compute one contact correlator, which is an n-point correlator, what you're supposed to do is to put another field here, choose its delta such that the sum adds up to D, and then take 1 point away to infinity, you will recover the non-conformal n-point correlator from the conformal n plus 1 point correlator. And in fact, what you can also see is you can take away this relation is through this limit of taking 1 point away to infinity, but you can get rid of that limit by inverting and then translating by xn plus 1 into this relation, and then you get an equality between the n-point non-conformal correlator and the n plus 1 point conformal correlator. The next couple of slides are not so important, but just to say that these conformal contact correlators are some objects that you can easily compute, and you can write down formulas for them, let's say at 4 points, 5 points, and so on. So we have some technology for how to be able to compute these conformal contact correlators in this Mellin space and so on that I won't get into. But this result is true for now for any Feynman diagram. Okay, so if you give me any Feynman diagram in this position space that you want to compute, I will add an extra field at each vertex so that the conformal constraint is satisfied at each vertex and take all of those points away to infinity in the end. So that's how you get flat space correlators as limits of conformal correlators. And now we will use this result to get to momentum space Feynman diagrams from conformal integrals. So how do we do that? So we come back to this one loop Feynman diagram in momentum space. And here you will see that the integral here is very similar to the position space integral. You're just, instead of integrating over some intermediate point in position space, you're integrating over this loop momentum. So it's the exact same integral. So one can import all of these results into momentum space. And if you do that, you get this relation here between one loop diagram with n plus 1 internal lines and one loop diagram with n internal lines. So that's the relation from the position space to momentum space. So in terms of pictures, so you get what I'll call conformal families. So at one loop, they look like this. So this diagram here, which is in all blue, is such that the deltas corresponding to the internal lines add up to the space-time dimension. So it's And if you try and compute this, you get a conformal integral. And from that one, you can get this 3-point general triangle diagram, which no constraints on the deltas. And so on for all the other polygons. So you can go on and do this at 2 loops. So this is a conformal double box from which you can get these 2 kinds of integrals. All the ones which are in blue are the ones where sum of scaling dimensions of the internal lines add up to the space-time dimension. And you get relations at 2 loop which look like this. You get something called the pentagon box family, which I like to better call the Yogi Bear family, and so on. So at 3 loops, you'll get a family like this. At 4 loops, you'll get something like that. Then let me tell you in the last couple of minutes that I have some exact results for Feynman diagrams that you can get via this method. The first example is this one, where we had how do you get a general triangle diagram. So exactly in 4 dimensions, if you want to do it, you get the box integral to be given in terms of this dialog. And to get the triangle diagram out of that in 4D, all you have to do is take these cross ratios and make them into simple ratios. The form of the answer remains the same. Okay, you just substitute the cross ratios with the simple ratios. Now, in fact, when I came up this, when I was looking at these relations, I was trying to look at the literature and see if this has been encountered in some form before. And if you look at massless phi-cube theory in 4 dimensions, these guys, David Ichev and Yusukina in 1972, they showed that these sets of diagrams, which are L-loop contributions to the 3-point and 4-point functions, there's a relation between them. And they actually computed exactly these L-loop contributions. In our language, it's very simple to note that once they computed the 4-point L-ladder diagram, you could have gotten the 3-point L-ladder diagram without doing any work, just by taking the cross ratios and making it into simple ratios. In fact, you can go one step further and compute the 2-point L-ladder at L loops, and you get this nice, cute answer, which matches with the 1-loop result that these guys computed in 1980 and some 3-loop and 4-loop results that were computed in this paper in 2010. You can also now look at conformal families I'll just take 1 minute more, in any dimension, not just, so that was for 4 dimensions, but now you can do it in any dimension. And you can get the general triangle diagram out of the general, of the conformal box diagram, and that takes this form. You can go ahead and do it for the general box diagram from the conformal pentagon diagram, and you get this answer. Now you can do dim-reg with this answer. You can put, you can put d equal to 4 minus 2 epsilon, and you'll get something like this. You expand out in epsilon so that you get it to any order in the dim-reg parameter. You can also get on-shell answers out of this very simply, because the way I defined it is a function of these 5 ratios. But if you wanted an on-shell answer, all you have to see is put the ones that are cyclic, P1 minus P2, P2 minus P3, P3 minus P4 to 0. So you'll only be left with 1 ratio, which is this P13 by P24. So you just have to do an integral over 1 ratio, and you can get an exact answer in terms of these 3F2 diagrams. And now it matches with this general result, which was computed in this paper, where they computed the massless on-shell box integral with arbitrary powers of propagators by the differential equations method. But for us, it is just doing 1 integral to get this exact answer out. So we can go and do that at 2 loops and so on. If you wanted to find this 2-loop diagram, you'll do it from this 5-point conformal double box diagram. So you'll get an off-shell and an on-shell answer for this. So with that, I'll stop, and I'm already out of time. But if you have any questions, I'm happy to take them.
So there was something that confused me. Let's say we look at the 2-to-2 scattering at 1 loop in 5-4 theory. Then at every vertex, I think your conformal dimension is adding up correctly. But we know that that diagram is UV divergent, so the answer should not be conformally invariant.
Right.
How do you see that here? I mean, if you shouldn't just be able to, I mean, in any case, you don't even need to add any external points here, right? So how do we see the fact that the answer is not conformal?
So in that case, it was already conformal in the way I was saying it, right?
It was already conformal, but the answer should not be conformally invariant.
Right.
You should see the UV divergence somewhere.
Right. Right. So if you write the exact answer out, you will see that there is a UV divergence. So so there I don't have anything more to say than how people would compute it, right? They would compute it, and then they show that there is a UV divergence in that answer. What I have to say, what is new in what I have to say is, how do you get the UV divergence from doing that integral, you can also get the UV divergence out in the phi cube theory. You didn't have to do a new computation there to get the same, to look at the UV divergence there. So you know, in your diagram, you have this 5 to the 4th theory, and so the conformal constraint is satisfied at each vertex. But I would take 2 points out to infinity, then I would get a 2-point diagram, which is in phi cube theory. But I would get the same UV divergent answer that you would have got. Yeah. Right. So I would actually be doing the computation in the phi cube theory. So what I would do is I would do it in the way that Suvrat said for the conformal answer. Then I would put d equal to 4 minus 2 epsilon and get the Dimmereg answer for the phi cube theory.
So in the interest of time, let's postpone discussion for after, but thank you so much for a great talk.
Thank you.